So here we are going to talk about beat frequency. Beats arise when there are two interfering sound waves with slightly different frequencies. And I particularly think that the pattern of beat frequencies just look amazing. So this is an example of a beat frequency that I've plotted over here. We'll come back to this plot and discuss this in a bit, but first let's talk about the idea of interference. So we are going to interfere two different temporal waves at the same location. So because they have the same location, we can just take out the kx part. So I'm going to try to talk about just the time part of these two waves. And so we're going to work out the details over here. So for beat frequency, we now have two time-dependent waves. y1t is equal to, let's call it y0 times sine omega 1t. And then we have the second one, y2t is equal to y0 times sine omega 2t. So these two frequencies, so the frequencies are f equals omega over 2 pi, and they're slightly different. F1 and F2 are not equal to each other, right? And so which means that this also tells us because f1 equals omega 1 over 2 pi, etc., which means that omega 1 and omega 2 are also not equal to each other. Okay, so we'll talk about the difference in frequencies delta f, which is equal to f1 minus f2, and this is related to omega 1 minus omega 2 because I can just plug in f1 equals omega 1 over 2 pi and f2 equals omega 2 over 2 pi. So I get omega 1 minus omega 2 over 2 pi. So this is equal to delta omega over 2 pi. Okay, good. So now what the question is, what happens when I interfere these two waves? Well, superposition will tell us that y of t is equal to y1 of t plus y2 of t. So now let's add these two together. So we get y0, and then I'm going to factor the y0 out. So we get sine of omega 1t plus sine of omega 2t, right? And I'll use my earlier trig relationship just to remind you. The trig relationship is sine theta 1 plus sine theta 2 is equal to 2 times sine of theta 1 plus theta 2 divided by 2 multiplied by cosine of theta 1 minus theta 2 divided by 2. Okay, so going back over here, then we get y0 times 2 times sine of omega 1 plus omega 2 over 2 multiplied by t times cosine of omega 1 minus omega 2 over 2 times t. Okay, so this is the amplitude of the resultant wave. In case of sound, you have to remember that sound, what do you hear, right? So what do you hear in your ears is the intensity. So hearing is the intensity, not the amplitude itself. It turns out that intensity is proportional to amplitude squared. So since intensity is proportional to amplitude squared, what you're really hearing is the square of this wave yt squared, right? So that gives us 4 times y0 squared times sine squared omega 1 plus omega 2 over 2t multiplied by cosine squared of, I'm just going to write this as delta omega over 2t. All right, so this is our sine and cosine wave product. So if I just go and look at the amplitude, right? So now I want to look at the amplitude as a function of time. So if I look at the amplitude as a function of time, this is what it looks like, right? So this particular plot has been generated for two different frequencies. And the frequencies that I chose in this particular plot are essentially f1 equals 100 hertz and f2 equals 102 hertz. So that the difference, so delta f is equal to the absolute value of f1 minus f2, so that's 2 hertz. Okay, so we're gonna call this definition delta f, the absolute value. You usually are able to hear difference in frequencies, but not always whether the frequency is negative or positive. So delta f equals 2 hertz is the difference in the two frequencies. And if you notice carefully, this the oscillation over here, that has a smaller frequency compared to the very rapid oscillations that are inside these the cosine wave. So essentially, that the fast oscillation, the rapid oscillation inside, that corresponds to this omega 1 plus omega 2 over 2 t, and the overlying the envelope curve is this cosine delta omega 2 delta omega divided by 2 times t, right? So that's the overlying the envelope curve. Okay, so now what is the frequency of this guy? Because we're hearing the amplitude squared. So what is the frequency of that? It turns out that the frequency of cosine squared is essentially twice the frequency of a cosine curve. So how do we see that? So here I have actually plotted a cosine curve. So the blue curve here is the cosine curve, and then I've squared the cosine curve and plotted it over here, right? So this is the square of my cosine curve. You can notice that when the cosine is 0, cosine square is 0. When the cosine is 1, the cosine square is 1. But when the cosine is also negative 1, the cosine square is still 1, right? So clearly these oscillations are happening faster. How fast? 2 times as fast as the original curve. So really, the frequency of this cosine square curve is really 2 times the delta omega over 2. That's the angular frequency, right? Uh, so if you call it beat angular frequency, yeah. So for the beat angular frequency, this is the result. So 2 divided by 2, that cancels, and so we get delta omega. And corresponding to this angular frequency, we have the linear frequency. So frequency is equal to delta f is equal to delta omega divided by 2 pi. And so this is referred to as the beat frequency. So beat frequency is the frequency of sound that you hear due to two different sounds interfering. But the interfering sound waves have slightly different frequencies, and the beat frequency is equal to the difference in the two differing frequencies that are interfering. All right, so that's it for beats. We are going to continue this discussion with traveling waves interfering with each other to form standing waves. So the next topic of discussion will be standing waves.